Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at biopotential electrodes and half cell potential of biopotential electrodes. And we said, why is this happening? Because of a charge double layer or double charge layer that is generated, and this causes a potential difference to exist between these two layers within the electrolyte. This we discussed. Another design consideration for biopotential electrodes is impedance. What is impedance? We know what is impedance. Impedance is resistance plus reactance, R plus Jx. Where J, what is J? J is the imaginary number. We know this. And we know X itself is frequency dependent. We know this. How do we know this? We know this from high school physics and from basic electrical engineering courses. We know this from our previous knowledge, right? Impedance is essentially the total opposition a given circuit offers to the flow of current. Note that it is not exactly the same as resistance. Impedance is a concept that is similar to resistance but not exactly the same. That is, resistance is the constant opposition that is presented to flow of current regardless of the frequency at which this current is flowing. This is resistance. Reactance, on the other hand, is a frequency dependent opposition that is produced due to capacitors and inductors, or due to capacitive and inductive effects in the particular circuit that we are working with. There may not be explicit capacitors and inductors, but there might be capacitive and inductive effects that might be there. That might be frequency dependent. Now, let us take a look at how to give an example. Consider flow of traffic through a road. Now, road width, assume that the road width is a constant. By the way, that also can change. Assume that the road width is a constant. Say in a national highway, the road width is a constant. Now, how fast you can go is limited by how wide the road is and the traffic flow, of course. But let us say there is a traffic light in there. The traffic light is a timing dependent component of opposition to flow, whereas the road width is a constant opposition to flow. If the road was infinitely wide, then everybody can go at infinite speed, very high speed. That is not possible. So, the constant opposition is resistance, and the one that is governed by timing and frequency is reactance. Something to a fundamental difference, but both are essentially impeding or obstructing the flow of traffic in the case of the car or the vehicle. In our case, this is essentially flow of current that is being obstructed or impeded. Now, what are the sources of impedance what is our interest? Our interest is not traffic light. Our interest is biopotential electrodes and biopotential measurement. What is the source of this impedance in the case of biopotential electrodes and biopotential measurement? Electrode-electrolyte interface essentially can form a capacitive double layer. I mentioned this previously. Especially at low frequencies, this reactance due to the capacitive double layer will be high, because unlike what one would expect, what is happening at the electrode-electrolyte interface is a charge double layer that is being formed, leading to capacitive effects that dominate at low frequencies. And some biopotentials of interest are having significant critical signal frequencies at low frequencies. One example is the electroencephalogram, which is having significant signal power below 50 hertz, for example, right. Then electrolyte skin interface. That is, so the skin itself adds a form of variable resistance, unpredictable variable resistance and variable capacitances to the, because of the skin layers. We discussed this, the layers of the skin, stratum corneum, stratum granulosum and stratum germinativum. There are 3 different layers and they offer different types of impedances. And then there are lead wires and connectors that also contribute both resistances and potential capacitive effects also they contribute. So, all of this put together, you actually have multiple dimensions that contribute to this impedance, which is electrolyte interface, electrolyte skin interface and lead wires and connectors that contribute this impedance. As I mentioned, impedance is frequency dependent, and at low frequencies such as those of EEG and ECG, there is a high impedance that is seen due to the dominance of capacitive effects. In relatively high frequencies, those that you see in EMG for example, impedance is low, but then it is sensitive to motion and noise. Why is impedance more critical in ECG than in EMG? Because in ECG, impedance is caused due to the low frequency effects. That is, this is something that you cannot get rid of. This is the nature of the signal, right. So, in the electrolyte, there is a series resistance and the series capacitance. This RW and CW are the Warburg resistance and capacitance. What is this Warburg resistance and capacitance? Check what this is. Check by yourself what is this Warburg resistance and capacitance. And I could model this electrode using this. I could model the skin using this simplified equivalent circuit. So, because of low impedance, because of low frequency in ECG, impedance becomes more critical in ECG than in EMG. Is there a better way to, reduce impedance practically? Well, there are ways. One is to use electrode gel. Another is to abrade the skin. Many times in EMG, what you do, you shave the hair, abrade the skin and apply alcohol and then put the electrode. Skin abrasion or skin preparation, let me simply call it as skin preparation. Abrade the skin, apply alcohol and then apply the electrode gel will ensure impedance is matched. What else can I do? I can try to have active electrode designs. In this case, I get a small amplitude signal and I amplify it then and there, and then have a post amplifier, a second amplifier that amplifies. This reduces impedance due to the lead wires, for example, right, or impedance due to the conducting wires. So, impedance is not only a factor in the electrode alone, impedance is a factor throughout. Impedance is a factor that is there in the lead wire, that is there in the cable, throughout. Impedance is there everywhere. These are some methods that I can use to practically reduce the impedance. What other ways can you think of? I will leave you with that question without answering you. I will leave you with the question of what else can you think of? A numerical problem related to impedance. A glass micropipette electrode filled with 3M potassium chloride has an internal resistance of 25 mega ohms and is modeled with a distributed capacitance of 0.1 picofarad per micrometer over the tip length of 800 microns. Question is, what is the capacitive reactance at 1 kilohertz? Very critical, because capacitive reactance is frequency dependent, and the total impedance magnitude at 1 kilohertz, also at 1 kilohertz. This is the question. What is the total capacitive reactance at 1 kilohertz, and the question is what is the total capacitive reactance at 1 kilohertz and what is the total impedance magnitude at 1 kilohertz. Now, I can find out this is a distributed capacitance. So, I can find out total capacitance C as 0.1 times 800, which is 80 picofarad. So many picofarads. This is the capacitance. Now, I can find the reactance. What is the reactance of a capacitor? The reactance of a capacitor is 1 by 2 pi f c. Is it not? Substitute for values of f is 1 kilohertz and c is 80 picofarads. What would be the answer? This would be 1 divided by 2 times pi into f is 1 into 10 power 3 into c is 80 into 10 power minus 12. So many ohms. That would be approximately 2 mega ohms, 1.99 mega ohms. How do I know this? Because I have already solved this. Okay, that is how I know this. Now, the impedance Z is resistance plus reactance. Is it not? What is resistance? That is 25 mega ohms plus jXc. Is it not? Plus the XC, and that is, you cannot simply add those two. Is it not? What I have to do is I have to find the square root of the sum of the squares, that is square root of 25 squared plus 1.99 squared. Is it not? That would be so many mega ohms. Not. What would that be? Use your calculator, scientific calculator, and you find that would be actually about 25.08 mega ohms. Check this, check whether I have solved this problem correctly. I think I have solved this problem correctly, but do check. Okay. With this, we come to the end of this video. In this video, we looked at impedance and solved an example problem of computing impedance at a given frequency. With this, we come to the end of this video. Thank you very much for your attention.